Hello learners, on behalf of Indira Gandhi National Open University, we welcome you for this video lecture session. Today's topic is steam jet refrigeration system. This is 39th module of the course Thermodynamics and its application. I am Subhashish Maji, professor in School of Engineering and Technology from Indira Gandhi National Open University. So, dear learners, let us begin our today's discussion on the topic steam jet refrigeration system. After listening to this video lecture, you will be able to understand the concept of steam jet refrigeration system and you will be able to solve the numerical related to refrigeration system. Let us discuss with the topic that is steam jet refrigeration system. This system, also called a flash cooling system, is generally used for chilling water. The system turns out to be an economical proposition in comparison to vapor compression refrigeration system. In such situations where steam to be used in the ejector of the system is available cheaply in large quantities. This is the schematic of steam jet refrigeration system. Here you see that there is a convergent divergent nozzle, and in the convergent divergent nozzle the steam is passed, and you know very well that when it is at the point of the lowest cross section, that is at the throat, where the velocity of the steam will be maximum. Now at the throat, since the velocity is maximum, so pressure will be less. Because of the low pressure, there is a vacuum created and the flash chamber, and in the flash chamber the water particle is falling just like a spray of water, and some water particle will evaporate and takes the latent heat from the water itself. Thereby the water temperature will be goes down and water will be cooled. The chilled water is pumped to the cooling coil where air is being cooled with the help of this chilled water, and that air can be circulated in an air conditioning system. After that, the water will again flow to the flash chamber and continue the same process. That means the water will be again evaporated, and that water vapor will go along with the steam which is passing through the nozzle, and because of the pressure decrease in the flash chamber, the water particle will evaporate, takes the latent heat from the water, remaining water itself in the flash chamber, and thereby the temperature of the water will be decreased, and that chilled water again it will pass to the cooling coil with the help of the pump, and after giving out in the heat exchanger, that is in the cooling coil, the air will be cooled down, and the water, after extracting heat from the air for cooling of air, that water will again pass into the flash chamber and the process continues. And if the process continues, the temperature of the water in the flash chamber will decrease. Water to be chilled is sprayed in the flash chamber. This chamber is well insulated and maintained at low pressure with the help of steam ejector, which continuously removes the water vapor flashing in the chamber. Because the chamber is insulated, the energy required for vaporizations, a part of spray water has to be supplied by the non-vaporizing liquid part. Hence, the temperature of liquid water in the flash chamber decreases to provide the required chilled water. The chilled water is pumped out to an external heat exchanger through the cooling coil, where it cools the air to be condensed. The water from the cooling coil is again passed to the flash chamber. As water vapor is being continuously removed from the flash chamber, there is a need for supplying makeup water to the system. The steam from the ejector is condensed in a large condenser, which is cooled by water from the local source. The condenser is maintained at the required low pressure, normally sub-atmospheric, by wet and dry pumps. Now let us take up a numerical so that our concept will be crystal clear. A refrigerator used R134A as the working fluid and operates on an ideal vapor compression cycle between 0.14 megapascal and 0.8 megapascal. If the mass flow rate of the refrigerant is 0.06 kg per second, determine the rate of heat removal from the refrigerant space. B part of this problem is the power input to the compression. Number C part is the heat rejection rate in the condenser, and lastly we have to calculate the coefficient of performance for this refrigeration system. From the R134A refrigerant tables, the enthalpies at the four states are: H1 is 236.04 kilojoule per kg, and S1, that is entropy at point 1, is equal to 0.9322 kilojoule per kg, that is equal to S2, because the process 1 to 2 is isentropic process. So entropy at state 1 has to be equal to entropy at state 2 for the isentropic process. Now this is the cycle diagram, that is pH diagram for exercise 1. Now here you see that point 1 is at the saturated vapor line, and the process 1 to 2 is the process, that is compression process, which is going on in the compression. Then 2 to 3 process is going on through the condenser, and the throttling process is going on from point 3 to point 4. And you all know very well that during the throttling process the enthalpy remains same. So it is a constant enthalpy process. So enthalpy at state 3 is equal to enthalpy at state 4, and the net refrigerating effect is H1 minus H4. The compression work is H2 minus H1, and the COP of refrigerant is net refrigerating effect divided by the work done. So COP will be H1 minus H4 whole divided by H2 minus H1. Now let us see how we can solve this problem by getting this data. Now the pressure P2 is equal to 0.8 megapascal. Entropy at S1 is equal to the entropy at S2, that is equal to 0.9322 kilojoule per kgK. H2 is equal to 272.05 kilojoule per kg, and H3 is equal to H4 because the process 3 to 4 is the process going on through the expansion device, and when there is expansion process is there, the enthalpy of the refrigerant will not change. So enthalpy at point 3 of the refrigerant has to be equal to the enthalpy at the point 4. That's why H3 is equal to H4, that is equal to 93.42 kilojoule per kg. Now Q2 is equal to 0.06 within bracket 236.04 minus 93.42 is equal to 8.56 kilowatt. WC is the work done onto the refrigerant by the compression is equal to the mass flow rate multiplied by the work done by the compressor per kg of the refrigerant. So WC is equal to 0.06 multiplied by 272.05 minus 236.04, that is equal to 2.16 kilowatt, and Q1 is equal to 0.06 multiplied by 272.05 minus 93.42, that is equal to 10.72 kilowatt. So COP is, and the net refrigerating effect is Q2. So the COP is equal to net refrigerating effect divided by the work done. So Q2 is the net refrigerating effect that you have already calculated, that is equal to 8.56 kilowatt. How you have got it? Because the net refrigerating effect is equal to mass flow rate of the refrigerant multiplied by, in this case, H1 minus H4. So all these data are given. You can calculate the net refrigerating effect Q2, and WC is equal to H2 minus H1 multiplied by the mass flow rate. So that you can also calculate for this particular problem, because H1 is known and H2 is known, so that comes out to be 2.16 kilowatt. So COP for this particular case is equal to Q2 divided by WC is equal to 8.56 divided by 2.16, and finally COP you will get 3.963. Dear learners, for solving any numerical, first of all we have to note down the data which is given for any problem. After that we will see how we can solve that particular problem with the given data. So this is another very interesting numerical, that is exercise 2. In an ideal air cycle refrigeration system, air enters the compression at 1 bar at 5 degrees centigrade and is compressed to 3 bar. The air is then cooled at constant pressure to 50 degrees centigrade and then expanded in a turbine to 1 bar. The cooling capacity of the system is 10 kilowatt. Assume air behaves as a perfect gas with Cp is equal to 1.005 kilojoule per kgK. Here Cp is the specific heat at constant pressure, that is given, that value is 1.005 kilojoule per kgK, and Cv is given as 0.718 kilojoule per kgK. The Cv is specific heat at constant volume. So Cp is given, Cv is also given. Find COP, that is coefficient of performance, mass flow rate of air and the power required by the system, assuming the efficiencies of compressor and turbine to be 0.7 and 0.75 respectively. Now, dear learners, let us see how we can solve this particular problem. But for solving any problem, if we draw the cycle diagram, either TS diagram or PV diagram or pH diagram, then things will be very simple for us for solving any problem on thermodynamics. Now, this is the cycle diagram. So, let us see the state point 1 is the entry point of the compression. Now, the point 2, which is shown by the dotted line, is the actual compression process, and there are some irreversibilities. Because of that irreversibility, we get the actual work, and the end point is given as 2 for the actual compression process. And here PL is the low pressure and the air is compressed from the low pressure PL to the high pressure pH. So PL is the low pressure for this compression process, and the pH is the high pressure for this compression process. So the air is compressed from the low pressure PL to the high pressure pH during the actual process, which is depicted in the dotted line from 1 to 2. Now, for the isentropic process, that is reversible adiabatic process, the process is from state 1 to state 2s, and here you see that during this isentropic process from 1 to 2s, the entropy is constant. There is no change in entropy in the adiabatic and reversible process, that is known as the isentropic process from state 1 to state 2s. Now, point 3 is the entry point in the expander or the turbine, and if it works isentropically, then the process from 3 to 4s, but because of the irreversibilities present in the process, the actual process is depicted by the dotted line from 3 to 4. So, the actual process is, for this particular case, is 1 to 2, 2 to 3, 3 to 4 and 4 to 1. But if we consider it is a reversible adiabatic process for the ideal case, then the cycle is defined as from 1 to 2s, 2s to 3, 3 to 4s and 4s to 1. Now let us see how we can solve this numerical with this given data. Now the cycle is shown in figure 2 here, while 1 to 2s to 3 to 4s to 1 is the ideal cycle, and both the compression and the expansion in the turbine are reversible and adiabatic process. But the actual process is different from the isentropic process or ideal situation. Then the actual process is 1 to 2, 2 to 3, 3 to 4, 4 to 1. This is the actual cycle. Now, what is the data given? Here the initial temperature before compression is T1 is given as 5 degrees, that comes out to be 278 Kelvin. The final temperature T2 is given as 380.5 Kelvin, T3 is 303 Kelvin and T4s is 236 Kelvin. Now, here you see that these temperatures, we will use the formulas which gives the relation between temperature and pressure. Now, the compression efficiency is given as the isentropic work divided by actual work, that is T2S minus T1 divided by T2 minus T1. But in this case, T2S we can calculate with the formula given between the temperature and the pressure. So, for if the air is compressed from T1 to T2, then we know very well that T2 by T1 is equal to P2 by P1 whole to the power gamma minus 1 by gamma. So, from that equation we can get the value of T2S and also T4S. Now, for this case, the compression efficiency is given as 0.7 is equal to the isentropic work divided by the actual work. So, the compression efficiency is equal to isentropic work done divided by the actual work done, that is equal to T2S minus T1 divided by T2 minus T1. But in this case, we know very well the temperature T1, the temperature T2S, the temperature T2S, that is for temperature T2S, that is 380.5, that we can get from the expression, that is T2S by T1 is equal to P2 by P1 whole to the power gamma minus 1 by gamma. So, gamma is, for this case, that is 1.4, that you can get the ratio of the specific heat at constant pressure divided by the specific heat at constant volume. So, for this problem, the specific heat at constant pressure is given, specific heat at constant volume is also given. So, the ratio that gives the value of gamma, that comes out to be 1.4. So, T2S is equal to T1 multiplied by P2 by P1 whole to the power gamma minus 1 by gamma. So, gamma is known 1.4, P2 by P1, the ratio, in this case, that is the final pressure by initial pressure, that is also known. So, you can get the value of T2S. If you do the calculation, you will get the value of T2S is equal to 380.5. So, the compression efficiency is given as 0.7, that is equal to T2S minus T1 divided by T2 minus T1. So, T2 you can calculate from this expression, that comes out to be 424.4 Kelvin. Now, similarly, the turbine efficiency is defined as actual work divided by isentropic work, that is equal to T3 minus T4 is equal to T1 minus T4S. So, in this case also, that you can get the value of T4S because there is a relation between T3 and T4S, because T3 by T4S is equal to P2 by P1 whole to the power gamma minus 1 by gamma. So, T3 is known and T4 you can calculate from that expression. So, after putting the value for efficiency of the turbine, the value for T3, the value for T4S, then we can calculate the temperature T4. That here it will see that the value of T4 is equal to 258 Kelvin, and it is the very low temperature. That's why the air at this temperature is capable of extracting heat from the refrigerated space to be cooled. Now, the COP of the air refrigeration system is equal to T1 minus T4 whole divided by T2 minus T1 minus T3 minus T4. If you put the value of T1, T2, T3 and T4, the coefficient of performance comes out to be 0.245. Now let us see how we can calculate the mass flow rate. The capacity is equal to mass flow rate multiplied by refrigerating effect. So mass flow rate is equal to capacity divided by refrigerating effect. So capacity is given, that is 10 kilowatt, divided by the refrigerating effect, that is Cp multiplied by T1 minus T4. T1 is known, T4 is known, Cp is known 1.005 because the value of Cp is given for this particular problem. So mass flow rate is equal to 0.497 kilojoule per second. Now let us try to calculate the power required. The power required is equal to mass flow rate multiplied by work done per kg. So the mass flow rate we have already calculated, 0.497 multiplied by Cp multiplied by T2 minus T1 minus T3 minus T4. So if you put the values of T1, T2, T3 and T4, the power required you can calculate for this problem, it comes out to be 40.65 kilowatt. Now dear learners, we have already discussed about the topic, that is steam jet refrigeration system. We have taken up some numericals on refrigeration cycle. So very quickly let us summarize our discussion. Today we have discussed the concept of steam jet refrigeration system. We had seen how the steam is being used for a refrigeration system, and by creating a low pressure situation so that the water evaporates, and when water evaporates, that takes the latent heat from the water itself, thereby the water is cooled, and that cooled water is being passed through a heat exchanger so that the air can be cooled down, and that air can be used for the refrigeration system, and after taking out the heat from the air, the water again circulates in the process. Thank you very much.